Okay, so this lecture is about practical transformer. So in our previous lectures, we have made a few assumptions when we have talked about an ideal transformers, and now we will be looking at those assumptions one by one, and we'll see how we incorporate those assumptions into the model of a practical transformer. So the first assumption was, we said that the winding do not have any resistance. Now we are saying for a practical transformer, the winding on both sides, the coil we're talking about, has an internal resistance, and that internal resistance is represented by the lumped resistance on both sides. So R1 is you can see that the resistance of primary winding, and R2 is the resistance of the secondary winding. So step number one, here we have incorporated the winding resistance, and this is 1 part 4 towards a practical transformer system. So this one is what we have as an ideal transformer. The ratio of the two turns is N1 to N2, and then we have R1 and R2 to represent the winding resistance. Number two, we assumed earlier that the core is made from a material which has infinite permeability, or we assumed that the reluctance of the core is 0. Now we are assuming that the reluctance is not 0. It's very small, but the reluctance is not 0. So what that means is, if we leave the secondary side open with no load conditions, the primary winding still draws some current, and that current is going to be our excitation current in here, IE. And it's made from two components. One represents the core loss, IC. The second represents the magnetizing current, IM. So the core loss component represents the magnetic core loss is the hysteresis and eddy current, and it's represented by this shunt resistance RC. And the second, the magnetizing component of this excitation current, is responsible for setting up the mutual flux in the core. And the effect is represented by this shunt inductance, and this is also known as the magnetizing inductance. So far we have incorporated the binding resistance. We have incorporated this branch in here, which represents your core permeability as a finite, and it represents the core loss and the magnetizing component of a practical transformer. Number 3 is about the leakage flux. So in case of an ideal transformer, we assume the whole flux just links to the core, but now you can see that some flux links through the air in here and here and here and here. So again, on both sides of the primary side and the secondary side, you have the flux phi L1, the leakage flux on primary side, phi L2, the leakage flux on the secondary side. So the impact of this leakage flux is represented by a series inductance. So this inductance represents the impact of the leakage flux. So this is a complete equivalent circuit for a practical transformer. So you have the binding resistance, you have the leakage flux, and you have the core loss and the magnetizing component of the current. So now we have to look at the two conditions. Number one, we will look into details of a no load condition. So how we can simplify this complete equivalent circuit into a simplified form. For the two conditions, number one is a no load condition. So under no load condition, what happens, or what we are expecting, that here the load does not draw any current or equivalent to 0, approximately 0. So that means current I2 is going to be 0. What that means is, so here you have I2 prime, which is basically your the current flowing in this part in here. So that's given by I2 divided by A, right? So since I2 is 0, so your I2 prime is also going to be approximately 0. What that makes is, this current I1 is going to be approximately, again, equals to only the excitation current. And excitation current is usually small with the larger values of these. So in that case, what happens is current flowing through this in here is small, so that causes a small voltage drop, small voltage drop, small voltage drop, small voltage drop. So what we can assume is that these components are not existing. So under no load conditions, we can simplify this equivalent circuit into a source, the primary side, and this shunt branch here. So representation of the transformer and the load. So R2, LL2, R1, LL1 can be assumed 0 under no load conditions. So the simplified diagram is looking like this in here. So we have, I just changed orientation to make sure that the diagram is clear. So now you can see that there is no resistance on for the binding and the leakage flux representation, and you only have this branch. And we have also drawn this circuit without, now you can see there is no transformer bindings represented here as well. So because this is referred to primary side. So what you have done is this was a part of the primary side anyways, and you have changed your V2 to V2 prime, and you have changed your I2 to I2 prime. So I2 prime is I2 over A, and V2 prime is A times V2. So this is transformer equivalent circuit under no load conditions, and it's referred to primary side. Now if you want it to represent in phasor form, so what we mean by phasor form, that all the quantities like the currents and voltages, they're going to have an amplitude as well as the phase angle. So you can do that as well. Usually the phasor quantities are represented by an arrow or a bar on top of the variable. So you can say that this is the phasor form for I, or it could be an arrow like this as well. And now in phasor form, they are going to have the phase angles as well as their values. So the very first, we're assuming one of them, for example, V1 variable, we're assuming is on the fundamental line of line here, and it's going to have a phase angle of 0. Now the current which flows through the resistor is going to be in phase with the voltage, because resistance does not contribute to any angle. At the same time, whenever a current flows through an inductance, it's going to be lagging behind the voltage by 90 degrees. Okay, and you can see that the IE1 is basically the phasor sum of IC and IM. So it's a phasor sum now. So then you can combine them to have your IE1. This IE1 has an angle with respect to V1 and has an amplitude which is given by through the Pythagorean theorem, IC1 square plus IM1 square, and the square root of that is going to give you an amplitude for IE1. And rest of the quantities you can put them in phasor form as well. So in phasor form, the main difference between the representation of the quantities is now they're going to have both phase angle as well as the amplitude.